Mm-hmm. I'm just checking. Um,
Hi.
yeah, Victoria might be on a meeting with like some union or board or whatever the other meeting is when I check.
Okay.
My plan would be like maybe to wait till 3:50, 3:55 ish.
That's fine. That's fine.
Begin at that time, yeah.
That's fine. Assuming I am recording this, if that's all right.
Yeah,
I
absolutely. Yeah.
decided to record this. Okay, good, good. So, hi, Mokhtar. Hi, Ella.
Hi.
Hello.
Sorry, I haven't been able to meet you face to face yet, but I will. I will come to Macomb eventually.
Yeah, many people, but this semester I'm teaching in person. 2 of my classes in person. Last semester I was not in Macomb.
Right, right. So, well, this is, yeah. Yeah, I know. First year is always a big adjustment.
Yeah, exactly. I moved here in January.
Hmm.
And-
Yeah, but that's not, yeah, that's not an ideal time to move when it's so cold.
Yeah, exactly. It was not ideal at all. It was so cold. And yeah,
Okay, well, but I'm just saying this might be a complete disaster. We'll see what happens. It's been raining here a little bit, so we might, hopefully the internet will hold up. And also you're gonna have, they're doing some construction outside, so you might hear that.
Hmm.
I might suddenly have to leave. I mean, I think I might have to leave uh mom and dad down the hall, and I think they're gonna be okay, but you never know. So I might have to leave you and have you work on a math problem or something.
Okay, yeah, I understand. It may be a complete disaster. It may not be. We'll see.
But at this, but you know what, I'm cool with it. Either way. I'm not gonna stress about that much because this is my, this is my last talk as a full professor, and so this is kind of like, oh, the heck with it talk.
Mhm. Yeah, yeah. Hi, Liam.
Hey, Leah.
Hi, Tom. How are you?
Okay, we're hanging in there.
I see you on 3 screens, Tom. That must be a record. There is a monitor here in front of me. There is one like to my right, and then there is a big one over there.
Uh-oh. Well, so you're saying that you saw me on TV. It didn't break?
Nope.
Well, that's good. Yeah, so is it, anyone else, you didn't get refreshments for the colloquium, did you?
No, I mean
Okay.
I'm the only one here, and I'm too lazy for that.
Oh,
So
that's all right. That's all great. I thought,
Mm.
but I mean, you guys can still afford like cookies, right?
cookies, yes,
Okay,
yes.
great, okay,
Coffee. Last week there was coffee. Yes. So
good, good.
And I'm sure there'll be donuts for the conference tomorrow, the teachers' conference.
Oh, that's tomorrow?
yeah,
Yes.
that's
Oh,
tomorrow.
wow. Okay, oh, good luck, everybody. Come back.
I'm so stressed about tomorrow.
Oh,
No, myself. There's gonna be so many people. It's about 150 teachers that they're gonna come.
oh, wow, that's
Yeah,
amazing. That's way up from what it was.
that's huge.
Yeah,
Yeah.
Mhm.
that's not gonna be something. Yeah, I had to do the high school math contest for almost 20 years. And we had like 150 people come to campus as well. So yeah, that's like, so yeah. When it's all said and done, you want to give yourself a good rest. So
Yeah.
let me just make sure that that this still, well, I guess we'll find out. Let me just check one thing here. Okay. It works. Hey, Boris.
Hi. Fyodor is muted.
Yeah, further, however, is not important. Important people are here on Zoom. Boris here, everybody. Nice to see everybody on Zoom. Victoria is here. So our speaker today is Dr. Tom Blackford. A fair warning that Tom might be recording some of the proceedings. So, like, if you not wish to be recorded, maybe like like face, maybe kind of like. Yeah, so just be aware that a recording might be happening. The speaker himself will remind us the title of his talk. It's an interesting one, and it's not really a word I am pronouncing much. That's so maybe without much delay, Tom, it's all yours.
Okay, thank you, Fedor. Thank you so much for that wonderful introduction. And it's wow, this is a little bit emotional for me because this is my last talk as I guess a full professor, but I hope to come back a few times as a professor emeritus and give some more talks. And I'll definitely do that as long as Chicks on the Square stays open. Okay, so so let me just share. We'll see how this goes. Okay. Just to give you a heads up, they are doing some construction outside. So it might be a little noisy for a while, and the things could happen, but and hopefully the internet holds up. So, but the title of my talk is called "The Squaters and Their Lockers," and I think probably before I might as well relieve the suspense right now, since Fedor wants to know what a squater is. So I'll tell right away. So, well, squaters we actually have seen them. This is a term I just invented on myself. Myself. So a squater is just a solution to a quadratic equation of this form. Okay, we've seen this many times: a squared plus bx. X squared plus bx plus c equals 0, where a, b, and c are integers, and the they're pairwise, they're relatively prime, and the discriminant of the equation is equal to 32. And so we call this a quadratic. In some other generations, we said it was a quadratic surd of discriminant 32. So nothing really new. We've seen them before. We've seen and the reason why I call them squaters is because a few years ago I had a short story, and it was called Squate, and it was really about a the square root of 8 sort of comes to life and starts talking to this middle school student. So now I'm sort of building on the story with that. And I mean, there's going to be a little bit of balance here, trying to balance between, what's fiction and what is mathematically true. But the idea here is that, and I'll probably also talk about where Platonism comes in. Plato was well, he was famous for many things, but he had part of his belief was that there were some ideas that were actually real, that they existed in their own realm, and in particular, those were that numbers sort of existed in their own realm. And I've just sort of taken that to the extreme, where say not only do these numbers exist, but they are kind of alive. They can talk to each other. They think, and they actually can form their own society. So this is not quite new. In some of the literature, if you read Flatland, was written over 100 years ago. And that was, that was an attempt to teach dimension theory, but it was also, it was just about a story about this flat world where the characters are shapes, and the shapes came to life. And then there's a slightly newer story called Numberland, where the characters were actually numbers. They were, positive integers. They kept the math pretty simple there. So I'm sort of so this is done before, but I wanted to do this to have some fun, and also maybe make number theory a little more see number theory in a different view. So so we have some examples of squares would be the square root of 8, because and negative square root of 8. So they're because they're both solutions to x squared minus 8. You can also have any integer plus the square root of 8. Also, you could have something like 7 plus the square root of 8 divided by 41, because obviously 41. Well, we can figure out what it is. We'll give a characterization in a moment. These are all examples of squaters, but these are not squaters. Okay.
Um,
Yes.
are you actually sharing screen? Because kind of it's being shared, but it's only on one of our monitors. Are you sure you did the share? And can we try it maybe again now?
I don't know how to do the share. I guess it just there's a share.
Well, I mean, there is a big green button in the
Right. I see it, and I'm using the advanced thing, to use my
right.
I don't know, because I'm using my second camera here. I mean, let's see.
Oh, you have two cameras.
Well, yeah.
Anyway, please continue. We'll see if we can switch monitors or something. So,
Okay, I'm sorry about that,
Now.
but
I can see it here. It's
Mhm.
okay, great. So these are not squaters, and we'll see why in a moment. Even though might look even involves the square root of 8, but it doesn't. But it might. Not all of them are squaters, because if you look at their corresponding minimal equation, it's something like this, but the coefficients are not all relatively prime. So first thing is that every squater can be written in this form, b plus the square root of 8 divided by a, where b squared minus 8 is equal to a times c for some integers a, b, and c, and we have this condition that a or c must be odd. Okay, so we have, and the reason for that is that that's all we need, because we can see any combination, any common factor of a, b, and c must divide 8. Okay, so it's either going to be 1 or a power of 2, and so that's what takes care of that. This is actually this would actually be a root of the polynomial ax squared minus bx plus c equals 0. And that, of course, is going to be, so a and minus 2b and c will be relatively prime as long as a or c is odd. And we all know how to solve quadratic equations. So if you were to just solve this using the quadratic formula, you can easily see that capital B here has to be even, so you can divide by 2, and then everything follows. So every square is going to be in this form, and this is kind of like the natural form they like to be in. So we're going to let script S be the set of these squares, these quadratic irrationalities of of discriminant 32. And we see that if alpha is a squator, or if alpha is an S, then so is its conjugate alpha prime minus negative alpha, 1 over alpha, alpha plus some integer, any integer, or 1 over alpha plus an integer. Okay, and it's not too hard. For example, alpha prime, or the conjugate is b minus square root of 8 divided by a, but we can multiply them both sides by the top and bottom by -1, so we'll have negative b plus the square root of 8 over minus a, and sure enough, we have this equation, minus b squared minus 8 is minus a times minus c. Okay, similarly, we can write minus alpha this way. 1 over alpha is b minus the square root of 8 divided by c, can be written this way, and so on. Won't write all the gory details of it, but it's not too bad. That's not too bad. Also, and Fedora, this kind of like goes back to your group of SL2Z, or actually something a slightly bigger group. If A, B, C, D are integers and they satisfy this relation, AD minus BC is either 1 or -1. It's generally linear transformation. This also preserves squators. So alpha, if alpha is a squator, then this quotient will also be a squator. And it's not hard, again, not too hard to prove. In particular, if any number of this forms a square root of 8 plus b over c square root of 8 plus d will also be in a squator. And in fact, we're going to see later that every squator can be written in this form. Okay. Now here we have some fun. Now we're going to have a little fun. Okay. So we're going to have you can call him our hero or our guide through this world. We're going to a number that we usually don't think too much about. 5 plus the square root of 8 divided by 17. And we're going to give this guy a name called Pipsqueatine. And yes, we are going to call him a guy. And we'll talk about how gender works in the society later on. But here's Pipsqueatine is this, and it's his on our calculator, his value is 0.460 ... and we say, who cares? It's not really terribly important as far as this talk goes. What is important is that he's a root of this equation, 17x squared minus 10x plus 1 equals 0. And that's along with his conjugate, 5 minus the square root of 8 over 17. But of course, we're going to give her a name. We're going to call him Pimsqueatine. Okay, the M is for the minus part. Yes, you may have figured out that in this society, the quadratic surds with a positive irrational part are considered the quote unquote males, and the ones with a negative irrational part are called the quote unquote females in this. Okay, but so that's how this works. And then there's also so they're kind of soulmates, he and his wife or his conjugate, however you think about it. There's the reciprocal. We also have some other people in his family is his reciprocal, which is 5 minus the square root of 8. We can call her Fimsquate. And of course, his numerator is the conjugate of his reciprocal, 5 plus the square root of 8. We call him Fipsquate. And then another close person in his family is his opposite. We'll call him M. Pipsqueatine. Okay. And they live they don't really live on the number line. They live in their own world called Squateland. And in fact, they live in a very nice street called 5th Street because they are all because of all these fives here. And they have 5th Street all to themselves. These people and a few other numbers, because these are basically all the squators where B is equal to 5 live on 5th Street. Okay, and so we have 5 plus square root of 8, 5 minus square root of 8, and then of course there's Pipsqueatine and his conjugate, and then not surprisingly, their opposites are on the opposite side of the street. And you'll see that, you'll notice that these people have these numbers have a kind of a bigger house, nicer house than the others, because these, you can see these have a denominator of 1. These 4 numbers are algebraic integers. And of course, as we know, Safety knows that algebraic integers are a little more special than just algebraic numbers. Okay, so that's why they have, and they're kind of like a bit of like an upper class in this society. Okay. And yes, I call this the Euler Highway. And now some of you are thinking, oh, Tom has really lost his mind. No,
Oh, I see, sir.
we just have, hi, Gregory. We were just, I'm just
Sorry.
having some fun. Okay. Well, what about, we know that, like integers have a very significant geometric significance, as do square roots. What would be the geometric significance of our hero, Fitzquatin? Well, the obvious one is this parabola here, right? We know that he and his conjugate are going to be the x-intercepts of this parabola, but this is kind of like if you were to look at the parabola, it's kind of like a very anorexic parabola. It's not very pretty to look at, and it's very thin. So we probably wouldn't assign this for a homework problem to our students. Another way you could think of as geometric significance is something like this, where if we were to have a stop sign, or not a stop sign, but some kind of sign which was 5 feet tall, and if we had a sign right here which with 2 feet on each side, well, and if we put that up, and let's say that passed code, and we were able to put it up, and for some reason, if we wanted to take a string and measure its height, and then for some reason we wanted to cut that string into 17 equal parts, well, Fitzquatin, that he's our guy, right? He's exactly what we would want, but no one really would want to do that, I think, in real life, right? Okay, but those are a couple of its possibilities. But he doesn't really have much of a life, because he's not a solution to any homework problem that math teachers have used. The math teachers do like using the other equation, x squared minus 10x plus 17. Those of the roots of that, of course, are Fipsquate and Fimsquate. And every once in a while, so some students will work on this homework problem, and they'll get the things mixed up in the quadratic formula, and they'll come up with him and his conjugate instead. And so that's how, and so he gets to observe humans that way, but for a very short amount of time. Okay, so he doesn't really have much of a life right now, anyway. Of course he is irrational. It doesn't mean that he has irrational thoughts. It's just that he's irrational. The decimal places, of course, decimal approximations go on forever. He can't be written as a fraction. And as a real simple direct proof, you could say if he were written as a fraction, like a over b, where a and b are relatively prime, he would have to, if this is a solution to this equation, multiplying by b squared, we get 17a squared minus 10ab plus b squared equals 0. And so, of course, that means that a would have to divide b squared, and b would have to divide 17a squared, which would mean that a would be either plus or minus 1, and b would have to be plus or minus 17. And so, and obviously these numbers are not equal to our hero here. Okay, so he's not rational. He's irrational. There were lots of other proofs that depend on other irrational numbers, but this is a direct proof. Well, and then one time, although he does dream, he does dream and he has kind of a weird dream. He's been having a weird dream lately. It's called let's make a deal. He dreams on let's make this deal, and if you are familiar with that show, it's the one where you have prizes between these 3 doors, and Wayne Brady here is asked which door do you want to choose. And we're kind of familiar with that because it's related to another math problem, but in his dream, Pipsqueatine is behind door number 2, and these other 2 squaters are behind door number 1 and 3. Well, wonder what that's all about. But he's been having this dream a few times, and he doesn't know what's going on, so he just doesn't really tell anyone about it. But let's see what's going on with that. Well, we'll see a little bit later. He has many forms. Pipsqueatine has many forms. Of course, he can be written this way as 5/17 plus 1/17 square root of 8. So it's nice and formal. He also can be written in terms of the square root of 2. And he definitely does not like this form. He doesn't like to be there's a lot of tension between the square root of 8 and the square root of 2, because the square root of 8 can too many times the square root of 8 is written as in terms of the square root of 2 like this. And while we teach that's a great way to, we teach our students to show how square root properties work. Squate thinks this is kind of an insult to be always defined in terms of his rival, the square root of 2. So, and consequently, the other squares don't appreciate these forms. There's a lot of conflict between square root of 8's tribe and square root of 2's tribe. But some other forms, we have, he's the reciprocal of 1 over 5 minus square root of 8. He can also be written as fractions like these. And basically, I think you can see what happened here. We just took this and we multiplied and divided by 3 plus the square root of 8 here. Who cares? Well, it's not that much of a big deal, except that whenever Pipsqueatine can be written as in this form as a square root of 8 plus b, or c square root of 8 plus d, where ad minus bc is equal to 1. Something interesting happens. We can do, rationalize the denominator. And so we get this BD, we have something plus something else times square root of 8 over something else. And of course, AD minus BC is 1. So if we, and we can do the same thing with, if we take the reciprocal of both sides, we get this, and do the same conjugation. If we equate the irrational sides of both equations, we get that 1/17 is equal to 1 over d squared minus 8c squared, and -1 can be written this way, and 5/17 can be written this way. As a result, we get the coefficients of Pipsqueatine's equation can be written in terms of a, b, c, d this way. And what that means, turns out that his corresponding binary quadratic form, 17x squared minus 10xy plus 1y squared, is in fact like an affine transformation or a general linear transformation of x squared minus 8. It can be written as dx minus by squared minus 8 times cx minus ay squared. Okay, so that means there's this binary quadratic form and x squared minus 8y squared, we say they're equivalent in a certain sense. And again, Safey Safey and maybe a few others are familiar with this equivalence of binary quadratic forms. Okay, so that just means that obviously this takes on the same values as x squared minus 8y squared, and we're going to be kind of interested in that later on. One more crazy form is this. Once again, Pipsqueatine can be written as the reciprocal of 5 minus the square root of 8. Well, 5 minus the square root of 8 is a little bit bigger than 2, so we can peel off a 2, and this is 2 plus 3 minus the square root of 8. And 3 minus the square root of 8 is actually the reciprocal of 1 over 3 plus the square root of 8. And 3 plus the square root of 8 is a little bit bigger than 5. And this will be 5 plus the square root of 8 minus 2. And then we can write this as 1 over square root of 8 minus 2, and rationalize this fraction as 2 plus the square root of 8 over 4. Okay, So then 2 plus the square root of 8 over 4 is a little bit bigger than 1. In fact, we can write it as 4 plus the square root of 8 minus 2 over 4. And that leaves us to with square root of 8 minus 2 over 4. We can factor the 4 in a certain way and cancel, and we get 1 over 2 plus square root of 8. And 2 plus square root of 8 can be written as, is a little bit bigger than 4. So this is going to be 4 plus the square root of 8 minus 2. We can write this as 4 plus 1 over square root of 8 minus 2 again, and to get, like we did before, 2 plus the square root of 8 over 4. So what happens is that our hero is going to be 0 plus 1 over 2 plus this number, but this number is equal to 5 plus 1 over something, and that something is 1 plus 1 over something, and that's something is 4 plus 1 over something. So we have this really weird expression here. Okay, and so we see that even though he can't be written as a fraction, he can be written as, looks like an infinite continued fraction. All right, and maybe you've seen this before, some of you, but looks like it right now, it just looks like gobbledygook, right? But let's just see if we try to make sense out of this expression, and we chop things off at the pluses, we get regular fractions, right? We get 0 over 1, and then we get 1/2. Then with the next level, we get 5/11, 6/13, 29 over 63, 35 over 76, and so on. And we can write down the sequence like this. And so we get these fractions, and I don't know if you can see any patterns here. That anyone see anything? Like if you just focus on just the numerators or just focus on the denominators, it's not quite as easy to see, but obviously, you can see that 1 plus 5 is 6 here, and 6 plus 29 is 35, right? But well, let's see what's so special about these. These are actually turn out to be much better approximations than what our things that our calculator can give us, and it's better in this sense. If you go back to that the corresponding binary quadratic form, 7x squared minus 10xy plus y squared, and if we plug in the numerator and denominator of each fraction here, something happens. We never get 0, but we get pretty close to 0. Okay, we get either 1 or -4, and it's going to turn out that that's about as close as we can get, because the values of this quadratic of this form are the same as x squared minus 8y squared. And you can see, there's a little proof that, or you can show that can never become 2 or 3 or -2 or -3, right? So, well, that's kind of interesting. Another interesting thing that happens is that if you focus on, let's say, this 2, this 13, 76, and 443, if you take 8 times that number squared and add 17, you always get a square. And similarly, if you take the other denominators, 11, 63, so on, if you square them, multiply that by 2 and subtract 17, you also get a perfect square. But I really won't be able to talk about the significance of this in this talk, but this is very important because this shows that 7, 2, 37, 13, and so on. These are all solutions to x squared minus 8y squared equals 17. And in fact, the 7 is 11 minus 2 times 2. That is this 7. If we take 11 minus 2 times 2, we get 7. 63 minus 2 times 13 is 37, and so on. So it seems like we can get both of these coordinates from the denominators of these fractions, which we call right now, we'll call Phipps-Steen's convergence, because they do converge, and they converge to him, to 5 plus square root of 8 over 17. But that's a pretty interesting sequence. And we're going to come back to that. Now, I haven't said anything about lockers yet. So I know you can, what do lockers have to do with anything? Well, this locker puzzle. Okay. And this is kind of like a variation of another problem that involved houses on a street. And it goes like this. A locker room consists of a single row of lockers numbered consecutively 1, 2, 3, and so on. And the sum of the numbers that come before my locker is 2 less than the sum of the numbers that come after. So if the locker room contains between 500,000 and 1,000,000 lockers, what is my locker number? And I could also throw in how many lockers are in this locker room. Okay. Okay, you say, okay, wow. Let's how do we even begin? Well, I'll say, let's look just at some of these examples. So what we have is every locker is going to have a left sum and a right sum. So the left sum, L, is just the sum of the lockers that come before the locker, and R is the sum that comes after. And what we want is L plus 2 to equal R. Okay. Let's just look at some examples. Okay. So if we just have a single locker, in the locker room, there's not much there. L and R are both 0, and this gap K is going to be 0. We have 2 lockers. Locker number 1 here, L is L. There's nothing on the left-hand side, so that's 0. The right sum is 2. Okay, so the gap is 2. So this is one example of what we're looking for, right? Because K is going to be equal to in that case. Whereas this 1 plus 8K, we'll see the significance a little bit later. If we go to the second locker, now the left-hand sum is 1, the right-hand sum is 0, and the gap will be -1 in this case. 1, 2, and 3, the number 1 is here, it's L is 0, R is 5, and K is going to be 5. And you can see this is actually, if we go down to the next one, we get another case. If we have locker 2 out of 3 lockers, the gap is going to be 2 again. So right now we've come up with 2 lockers with this certain property, but we're nowhere near 500,000 lockers, right? And hopefully we don't have to do this, but we can see this how this goes. Well, all the various gaps, okay, here. And one thing that you might notice that we have gaps of 0, -1, and 1 and 2, but we don't have any where K is -2. All right. So we're going to see why that is true, and we're going to also see the significance. Why do we care about what 1 plus 8K is? Okay. Well, the reason why we care about this is, well, let's try to solve this problem using something called what we call the equation of a locker. Okay, so we have locker number n out of capital N lockers in the locker room, and we want to solve the equation L plus K equals R. Let's figure out what this is. So we're adding in the numbers 1 to n minus 1 plus K is equal to the sum of n plus 1 plus n plus 2 up to capital N. And we can of course, we can write this as this sum minus this sum. And using the formula for the sum of the first n integers, which if you believe the story about young Leonard Euler, he proved that while he was in class, but I'm pretty sure lots of others proved it before him. The 1 plus 2 plus 3 all the way up to n is n times n plus 1 divided by 2. This is what we call the nth triangular number. So plugging this in, now this equation becomes this, n minus 1 times n over 2 plus k equals capital N times capital N plus 1 over 2 minus n plus 1 over 2. And doing a little algebra here, bringing the little n terms over and cleaning things up, we get n squared plus k is equal to a triangular number. I mean, in particular, if k is 0, then we're talking about a triangular number, which is also a square. Where a lot of stuff has been written about those square triangular numbers, but this is kind of like a generalization of that. And now we can multiply both sides by 8, add 1 to both sides, factor. This is 2n plus 1 squared, so now we have 8n squared plus 8k plus 1 is something square as a perfect square, and we can rearrange this so that we have 2n plus 1 squared minus 8n squared plus is equal to 1 plus 8k. And this is what we call, this is the equation of the Locker. This is what is, so every locker, it depends on the locker number and also how many lockers are in the room. And what we want to do is we want to find a capital N and a little n for which this is true, when k, and in this case, when k equals 2. To keep this in mind, 2n plus 1 and little n might not always be relatively prime. So if d is their greatest common divisor, we can factor out a d squared from both sides, and we'll get something like this: x0 squared minus 8y0 squared equals some new number, capital K0. And the thing about this is that this x0 and y0 is relatively prime. And what this means is that this is a primitive solution to the equation x squared minus 8y squared equals some constant. Primitive means there's, the numbers are relatively prime. So once again, for our puzzle, we're trying to find an n such that 2n that this is equal to 17, or more generally, x squared minus 8y squared is equal to 17. Now, and if you were paying, if we looked at some of the observations we had from the sequence, we got a lot of, there was a lot that we already got some solutions to this, just not very many, as big a solutions as we want. Turns out we can, once we have one solution to this equation, we can get another one pretty easily. And that's right here, is that if xy is a solution to this x squared minus 8y squared equals k0, then so is 3x plus 8y, x plus 3y. And we say that we call these a kind of equivalent. Maybe equivalent is not the right term for it, but they're in the same class, let's say. One is kind of obtained from the other. And the way it happens is it's like this: x squared minus 8y squared can be written as this product, x plus y squared of 8, x minus y squared of 8 equals k0 squared. And then this can be written, we can multiply both sides by 1. 1 can be written as 3 plus square root of 8 times 3 minus square root of 8. These are actually two very important players in our story. In Squateland, but I digress. We can we can rearrange the factors, multiply them, and we see that that 3x plus 8y and x plus 3y are indeed our solutions. Okay, so we get a in fact, we get a whole class, an infinite class of solutions. It can be described this way, where we have, these are the points x, y, where x plus y square root of 8 can be written as some power of 3 plus square root of 8 times what we can call a primary solution, coming from x0, y0, where x0, y0 is in this certain range, and I don't have time to like explain it, but basically in this class, every solution corresponds to some power of 3 plus square root of 8 times some of this number that corresponds to a primary solution. All right, now this is one way we could go about this, but I want to give you going back to that really weird that expression we had, that infinite continued fraction. I want to like sort of pull the curtain back and talk about continued fractions and give you a crash course in that. Because we learned a little bit about, you might have learned a little bit about in grad school, but here goes. So if we start off with integers, u0, u1, u2, and so on, where un is going to be greater than or equal to 1 for n greater than or equal to 1, we can define these following rational functions, where u0x can be written as u0 plus 1 over x, and then we can replace x with u1 plus 1 over x and get another rational function, and then we can replace this x with u2 plus 1 over x, and then we get another rational function like this, and we can keep doing that, where we're just replacing the x in the previous rational function with un plus 1 over x. And this is how we get these finite continued fractions. Right now, these are just rational functions, but we can actually write them as normal rational functions or normal looking rational functions if we when we define some accompanying sequences. P's, we're going to mind our P's and Q's, and we're going to define the sequence Pn, where P negative 2 equals 0, P 1 is P negative 1 is 1, and Pn is equal to un Pn minus 1 plus Pn minus 2. And we can define the Q's similarly. So we note that the Q's are always going to be positive, because Q0 is going to be equal to 1, and it's going to be, that's less than or equal to Q1, which is strictly less than Q2 and Q3. So the Q's are going to be a strictly increasing sequence of integers. Now, there are several properties that obviously we don't have time to prove, but this is a crucial one. Pn times Qn minus 1 minus Pn minus 1 Qn is always a power of negative 1. And then this rational function that we defined above can be in fact written as Pnx plus P sub n minus 1 over Q sub nx plus Q sub n minus 1. If we replace, if we can plug something in, we can make a substitution, and then all of a sudden we get that this expression u sub 0, u sub 1, u sub n is actually equal to P sub n divided by Q sub n after a substitution. And every rational number can be expressed as a finite continued fraction in fact exactly two ways. And let me just go ahead and just show you, give an example, because it's kind of important later on. So if we wanted to do this with 41 divided by 16, we could use the division algorithm many times. We know how to use the Euclidean algorithm or the division algorithm this way. And so 41 is 2 times 16 plus 9. 16 is going to be 1 times 9 plus 7. 9 is going to be 1 times 7 plus 2. 7 is going to be 3 times 2 plus 1, and so on. And then we can just sort of go back and say, all right, 41, this should actually be 41. 41 over 16 can be written as 2 divided by 9/16, which can be written as the reciprocal of 16/9. And then 16/9 can be written as 1 plus 7/9, which is 1 plus 1 over 9/7, and so on. So following everything we have is we get that the 41/16 can be written this way. And again, what we're really saying is that 41/16 can be written as 2 plus 1 over 1 plus 1 over 1 plus 1 over 3 plus 1 over 2. Okay, that's what we're saying. And here I've computed the PNs and QNs. And something very nice happens. You'll see that 41 times 7 minus 16 times 18 is actually -1, and we can multiply things by -1. And actually we can get, this is really nice. We can actually write, we know that because 41 and 16 are relatively prime, we can write 1 as a linear combination of them. But now we can do that with all that stuff without doing all that substitution crap. Okay, with the continued fraction just gives us this right away. Okay, so that's kind of nice. But so every rational number can be expressed as that. There are actually 2 ways you could actually rewrite that. You could actually write this as 2, 1, 1, 3. 2, of course, could be written as 1 plus 1. So you could write it that way as well. Convergence, the convergence follow this inequality. It actually, comes from this property number 6, where, where the even indices of convergence are increasing, and the odd convergent indices are decreasing. And as a result, because this gap is always getting smaller, because these Q's are getting bigger, so this difference is getting smaller. So from the nested interval property, or some other properties in complex analysis, we can see that these convergences, in fact, will always converge to some number alpha. And we can write alpha this way. And we write it this, we can write, what we're saying is we can write alpha as a continued fraction. And we say that Pn over Qn is the nth convergent of alpha. And if alpha can be written this, and if we define alpha n to be this continued fraction, starting with un plus 1, and so on, we get some nice properties. Alpha n is going to be un plus 1 over alpha to the alpha sub n plus 1. U sub n is always the greatest, the greatest integer less than or equal to alpha n. And alpha can be written in this form using what we had before, using our property number 2, I guess. Every rational number can be written as an infinite continued fraction in exactly one way. If beta is irrational, we can do it. Basically, what we can do is kind of what we did with our hero Phipps-Quateen. We subtracted the greatest integer less than or equal to that number, and then take the difference, and then take the reciprocal and start again. So if beta is irrational, we subtract u0, take the inverse, and then repeat. Okay, and that's how we get this. Number 10, we'll skip and 10 and 11 we're going to skip right now because we're running out of time. But I can send you all these notes a little later on. So let's look at some examples of how this would work. The continued fraction representation of E can be written this way. So it looks like there is a nice pattern for E, even though E is irrational. Pi, not so much. Okay, there's no obvious pattern there. Square root of 2 is 1 followed by infinitely many 2's, which we can write like this. The square root of 3 is actually 1, and then it's followed by 1, 2 alternating back and forth ever since, from that point on. The golden ratio, 1 plus the square root of 5 over 2, that has the simplest continued fraction. This is just all ones. And the square root of 8, this is kind of important. It can be written as 2, 1, 4, 1, 4, 1, 4. So the 1, 4 is in. And you will see this phenomenon happens with a lot of other squators. You have 2 plus the square root of 8 over 4 can be written as 1, 4, 1, 4, 1, 4. 2 plus the square root of 8 is 4, 1, 4, 1, 4, 1. Here's our hero. Our hero Pipsqueene can be written as 0, 2, 5, 1, 4, 1, 4, and so on. And you'll see that all of this happens. Whenever we have a quadratic surd of the discriminant 32, the continued fraction is always 1, 4, ends in 1, 4, 1, 4, 1, 4. And more generally, if we take any irrational solution of a quadratic equation and we look at their continued fraction representation, the representation eventually becomes periodic. Okay, and that's a really big deal. It was proved by Galois, and we of course we don't have time to do that, but to prove all this. But we'll just say that there is a squator that for every squator can be the continued fraction is going to be like this. Now, what that means is for some alpha, if this is u0, u1 to un, alpha n plus 1 is going to be 2 plus square root of 8 over 4. Okay, so let's see why do we care about what happens with that? Well, if alpha n is 2 plus square root of 8 over 4, it can also be written as 1 over square root of 8 minus 2. And then because of our properties, if this is our squator, this can be written as p sub n, and we can just replace alpha n plus 1 with this number. We can do a little algebra, and when the smoke clears, because of all the properties of the p's and q's, we get that this is equal to some integer b plus negative 1 to the nth power times the square root of 8 over this q sub n minus 2 q sub n minus 1 quantity squared minus 8 qn minus 1 squared. So if we equate the rational parts, we get that we actually get a solution to this equation, x squared minus 8y squared equals plus or minus a, namely this, the q sub n minus 2 q sub n minus 1, comma, q sub n minus 1 as a primitive solution to this. So I am really kind of running out of time. So let me just show you, and what we're really trying to show here is that if we kind of have let me just get to the big theorems. Well, going back, what I'm trying to say is that if we take if p is prime, we can say that x squared minus 8y squared equals plus or minus p for some xy. This happens if and only if b squared is congruent to 8 mod p has a solution. And in particular, not only that, but then in that case, x plus 2y, y must be denominators of some consecutive convergence of some number in the form of b plus the square root of 8 over p, or b minus the square root of 8 over p. Didn't really, there was just so much I can't prove this, but we can, because if we have, if this is enough, to show that b plus the square root of 8 divided by p is a squator. And because of that, then it can be written as Pn, in this form. And then from there we get a solution. Okay. So this is this, I know that there have been some other proofs of this where they go they appeal to ideal theory or unique factorization in fields. But I kind of like this, because this actually, you can see what's going on. You can actually see see what the solutions, they don't just exist theoretically, you can see what they are. You want to think of another way of thinking about a quadratic irrational is you can think of it as a seed, and the fruit that it produces, it grows into a plant, and the fruit it produces are solutions to equations. Now, let me just go back, because I know we're really running out of time. We go back to our puzzle, then we were trying to solve this solution here, 2n plus 1 squared minus 8 squared equals 17, of either, and if we go back to the continued fraction representation of this, we can see that we can get, here are our P's, here are our Q's, and we said that 2, 13, 76, 443, they were all correspond to solutions, and they are actually going to correspond to these lockers that we're looking for. And if we were to keep doing this, we can see that these numbers keep getting bigger and bigger. These circled numbers would increase and go all the way up to 511, 223. And it turns out that that is actually a solution, that at 8 times that number squared plus 17 is this, this big number, which is really going to be our 2n plus 1. And then if we solve for capital N, we get this number. So our answer is that the locker number is 511,223, and the number of lockers is 722,978. Now, let me just say that, if you can give me about maybe 3 more minutes, Fedor. We have some examples here. We said before, there doesn't seem to be any locker where L minus 2 is equal to R. And the reason for that is that that would mean that we'd have to have a solution here. Our 8k plus 1 would be negative 15. And this would mean that x squared is congruent to 8y squared mod 3, because 3 divides 15. And 8, of course, is congruent to negative 1, so you have x squared is congruent to negative y squared mod 3. But of course, negative 1 is not a square mod 3. Okay, the only solution for this would be is if x and y were both 0 mod 3. Which means that 3 divides x and 3 divides y. But the problem with that is, if we have, that would mean 3 divides this, and 3 would divide this. That would mean 9 divides this, 9 divides this, but 9 does not divide 15, right? So we know that whenever we have 3, this 3, that packet, whenever 3 divides 1 plus 8k and 3 squared does not divide 1 plus 8k, there's no solution. And that's where the quadratic reciprocity comes in. And you can replace 3 with any prime that's congruent to either 3 or 5 mod 8s. Okay, that's quadratic reciprocity, which we didn't have time for. Another example, if we wanted to find lockers with a gap of 20, what we would do is to, 8 times 20 plus 1 is 161. And so we'd be looking for solutions where b squared is congruent to 8 mod 161. There are actually 4 of them. So we get 13, negative 13, 36, negative 36. And we actually get those correspond to these 4 squators, these 4 quadratic irrationals. And then we can take their continued fractions, and then we get and look at the corresponding solutions, and then the values for n. So like here, we get that for this first one, with 51 minus 2 times 10 is 31. And you can check that 31 squared minus 8 times 10 squared is 161. This 31 is our 2n plus 1. So capital N is 15 and n is 10. So that would be one set of solutions. And then this was the solution that we looked at when we were looking at our examples. And we get some others. Now, to find the squator in your locker, I did this with a friend of mine. I said, okay, you tell me which locker number you have and tell me how many lockers are in your locker room. And fortunately, there were only 20. So if you want to find this, what's the squator that corresponds to this, we can take 2 times 20 plus 1 is 41. So this is our 2 capital N plus 1 is 41. So the the locker equation would be 41 squared minus 8 times 16 squared is equal to negative, in this case, negative 367. But way we can do this, a little trick here. We can take the continued fraction for 41/16, which we just did before. And that if you take these last 2 numbers and multiply them, and then take these 2 bottom numbers and multiply them, 18 times 41 minus 8 times 7 times 16, that turns out to be negative 158. And we can put that negative 158 here. There are 1, 2, 3, 4, 5 numbers in the continued fraction. So if 5 is odd, that's when we put a minus square root of 8. And then negative 367 comes from here. And this is actually going to be the squator that corresponds to this locker and all the equivalent lockers that have this property, which have a gap of, in this case, negative 367. Okay. So I just said, okay, this is in we'll just give this squator a name, and we'll just call him Oscar. And our friend thought that was a little funny. So this is what we mean by it. So we can think about this as squators as all these squators have their own locker. And of course, they actually have infinitely many lockers. And there are actually some squators that have the same set of lockers. So what my story is I'm going to be working on in retirement is I'm going to try these where these squators are alive and they observe humans by watching them through their lockers and all the hilarity that follows from them. Okay. And I am so sorry because I really wanted to give you the proofs and all that. I can send you these notes a little bit later, but I think this would be a kind of an interesting exercise for high school students is just to try to find what's the squater in their locker giving this. So I know that this was a lot. Let me just show you one last slide. Okay. Where we say goodbye, WIU. I love you all, but I will be back. So, thank you.
Thank you, Tom. Fascinating. Zoom people, would you take care of the questions and would you start the question?
Yeah, Tom, is there anything special about that quadratic form, x squared minus 8y squared, compared to, say, x squared minus 2y squared?
Yes, very good, Safi, because I'm glad you brought that up. X squared minus 8y squared, and x squared minus 2y squared. First of all, they take very different values. The values are different. This you could have -2 as a you can't do that with x squared minus 8y squared. Okay, it won't work, because if you try to do that, let's say, and reduce things mod 8, then you get x squared is
Sure.
going to go into -2 mod 8. So there's no solution. But actually, the solutions to here actually can be, and also we also have another quadratic form, minus x squared plus 8y squared. Okay, these two forms, they have some values in common, but there are some their own unique values. So this is why it's quite different than like the binary quadratic forms like that are associated with the class group, where you're just working from the standard of a quadratic number field, and that's it. These actually sort of correspond to what we call quadratic orders. So
Right, right,
yeah, so
right. Thanks, Tom. Yeah.
sure.
Tom, if I may, I would have a question. Like, you had some equation of integers, and you showed like a class of solutions that basically we can do something and get another solution, and then like get another solution. Is there a for that equation? Is it just one fundamental seed, or it has some not overlapping classes?
They have the classes are separate. I mean, the classes are separate. However, the number of classes depends. It depends on. It basically comes back to 1 plus 8k and how this factors. So, like, for example, 161 is 7 times 23. Okay, so you're going to get. That's why we get four solutions for b squared is going to 8 mod 161. Okay. And those that corresponds to four quadratic irrational, 4 squaters, and four separate classes of solutions. And that 3 plus square root of 8 is really, we didn't have a chance to talk about it, but like when we had the when we were talking about the continued fraction representation of our hero here, we had, okay, so this corresponded to 7, 2, and this was 1363, and this corresponded to 37, 13. 37 plus 13 square root of 8 is actually 7 plus 2 square root of 8 times 3 plus the square root of 8. Okay, so actually these solutions are kind of related by the 3 plus square root of 8 things here.
Interesting. maybe let's thank our speaker one more time. Thank you, Tom.
Yeah,
Thank you.
thanks, Tom. It
Thank
was
you.
a
And
nice talk.
I'm so
Yeah.
sorry. I didn't put, I had so much stuff prepared and I just there's not enough time. I guess I'm gonna have to come back and give another talk, right?
We will be happy to
Yeah.
see you, Tom,
Mhm.
anytime.
Likewise,
Mhm.
likewise.
Great, Tom. I
Yeah.
hope we will see you soon. You're gonna come
Okay.
over.
You just tell me when you want me, okay? And I'll work around that.
Right, like at the end of the semester, you were thinking
Yes.
about,
Yeah, go ahead.
okay. Okay, be nice to see you.
Yeah, I mean, yeah, we'll talk about that because yeah, because I know yeah, we'll talk about that.
Right, thanks again.
All right, thanks, Tom.
Have a good
time. Yeah.
evening, everyone.
Yeah.
Thanks. It
Bye.
was
Thanks,
beautiful.
Tom. It was nice
Bye.
to see
Okay,
you.
Gregory, when are you, don't forget to raise
I should.
and write your book, okay?
Yep.
Thank you, everyone.
Thank you, everyone, for
Okay.
sure.